things like this.
Okay, hi everyone. Thanks so much for coming. Very glad to see so many people here, also from so many different fields. Very excited to present Professor David Stainforth, who's come all the way from Oxford to talk to us here. I've got a bit of an introduction for you, which is that David's a professorial research fellow at the Grantham Research Institute at LSE, and also an at the University of Warwick. And he carries out research on climate science and its relationship with climate economics and policy, especially uncertainty analysis and how academic assessments can better support decision-making in the context of climate change. And the reason I reached out to him is because he's the author of the book Predicting Our Climate Future. And I read that about 2 years ago. It completely changed my understanding of the climate challenge and really emphasized the importance of multidisciplinarity. So it's great that we have so many people here to have a conversation about this very important topic. So I think the talk will last an hour. We have some time after for questions. If you do want to ask something throughout, do feel free as well. But we'll also have time to discuss from, I think we've got the room till like 7 or so. So that should be great. And afterwards, if you want to join us at the pub, we plan to go to the Granta around 7 p.m. So I think that's all. Without further ado, hand over to David.
Thank you. Thanks so much for inviting me. It's great pleasure to be here. I must admit, I thought we had an hour for the whole thing. So I had in my mind that we'd be talking for about 45 minutes. But if I actually look at the time series of the length of my talks, I never keep to time. So probably quite good that we've got an hour. But also just to reinforce that statement, do just interrupt, put up your hand if there are things you want to expand on as we go through. That's absolutely fine. So yeah, thanks for inviting me. I'm going to talk about my book. So my book, of course, so the subject is climate change, which is a bit depressing, but put aside the sort of worries and the concerns about climate change, and I think climate change raises some of the really most interesting, some of the most foundational conceptual issues in science today about how we understand world, how we integrate knowledge, and how we use that information in wider society. So when I think about what I'm trying to do with my book, my sort of number one thing was to raise what those challenges are, just sort of highlight why understanding climate change is so difficult, and what are those big questions that we need to really grapple with. So the aim of the book partly is to say, this is interesting. This is just an interesting topic that you should be interested in, whether or not you're concerned about the consequences of climate change. And for that reason, I tried when I was writing this to not put myself into a particular category of concern. Because there are lots of books out there that say be very concerned about climate change. There are quite a lot of books out there that are saying don't worry about climate change at all. It's a big hoax. And I wanted my book to be one of the small number of books that sits in the middle, that would be able to appeal to either side of that argument, of that debate. And that turned out to be a really difficult thing to try and do. But that's what I was trying to do. You'll have to, if you look at the book, you can decide whether that achieved that. But sitting on the fence like that isn't something that I could do throughout the book. So I start the book in the sense of saying, well, I don't want to say which side I am on, but by about page 50, I think it is, somewhere around there, I sort of say, look, I've got to come out and say, where do I sit on my level of concern? And I am deeply concerned about climate change. I think the risks and uncertainties just make it more concerning. And at that stage, I give an 11-paragraph summary of why I think we know that climate change is an important issue for us. But I'm not going to deal with that today. I'm assuming that's not really terribly interesting to you. I don't want to go through that. It's kind of boring. It's kind of basic. What is much more interesting is the uncertainty, the challenges, and that's what I'm going to deal with today. So part of it is about why understanding climate change is foundational, conceptual, and interesting. But of course, it's also about climate change is essentially something that influences society, that society needs to respond to. So climate science needs to address that. And so the other aspect of my book was trying to put across how I see climate change as fitting together, to identify the strands of knowledge that we can say are robust and separate those from the strands of knowledge that are not robust, but very much in a conceptual way. So I'm not saying we know this and we don't know this, but I'm saying this is how we need to look at the problem, and this is how we might be able to get robust information if we accept those issues. And I understand that most of you in this audience have an engineering background, and if I reflect on that, I think when we're thinking about responding to climate change, building the energy transition, if we're trying to build barriers, we're trying to build new energy infrastructure, just build new infrastructure of all sorts. We build new schools, we build new homes. We want those things to last. We want them to be robust over the next 50, 100 years or more. And that means they need to be robust to the climate that we will have at that time. So we really want to know what we know about the climate at that time. Try to give the tools to people like yourselves to be able to critically evaluate the information that is out there, because there's an awful lot of information out there on climate change, and there's information out there that would give you the sorts of information about the changes locally on rainfall patterns, on temperature patterns, which would appear to help you build your robust infrastructure, plan your society. And I will be arguing today that a lot of that information is not as robust as you might think it is, and we need to be looking at different ways of providing that information and of using the information that's out there. Okay, so that's the kind of background, but let me start with the sort of big questions about that way to tackle it. What should we do? What's our target? How fast should we act? And there are various answers you could put to that. So one of the answers would be that we have an overarching goal of holding the increase in global average temperature to well below 2 degrees above pre-industrial levels. That was the conclusions of the Paris conference. So the Paris meeting was one of the conference of the parties of the signatories to the United Nations Framework Convention on Climate Change, which arose out of the Earth Summit back in 1991. And so we have these COP meetings every year, and of course there's going to be one in a week or so's time in Brazil. But big one that tends to be highlighted is the Paris one from 2015, where we had this agreement of trying to keep levels to 2 degrees, or better still, to limit it to below 2 degrees above pre-industrial levels. Pre-industrial levels being taken as before 1750, but really before 1900 is pretty much the same. So that's one type of policy, one type of target. Let's keep global warming to below 2 degrees. Another would be to say that we're going to try that's what we have in the UK. So due to the Secretary of, it's in UK law, it's a duty of the Secretary of State to ensure that the net UK carbon account for the year 2050 is at least 100% lower than the 1990 baseline. So we have that in UK law to achieve net zero by 2050. So that will be another type of target. And you can imagine extending that more broadly. Say, okay, maybe we should have a target to achieve net zero globally. So these are different sort of targets that we can have, but of course they're targets. Targets aren't necessarily met. Laws can be changed, and indeed, when we think about this one, the Conservative Party at the moment now has a policy to repeal this this law. So it might have it as a law, but it's not necessarily something that we can rely on. And targets such as the Paris Agreement of 2 degrees, it's a very nice target, but will we achieve it or not? That's very much open to question. Yeah, and we can talk about our own opinions about that later on. The point about that is what we need to do is think about how bad would it be if we don't achieve. We can set these targets, but if we don't achieve them, how bad would it be? Because assessing how bad it might be if we miss those targets gives us a way of evaluating how concerned we are, how much should we spend in order to achieve those targets. How big a deal is it? Does it matter if we miss it to some extent, and if so, how bad? How much can we miss it by and still be kind of acceptable? That, to me, is a kind of crux of climate policy. These are policy questions, the society questions, but the crux is to say how bad, what level of should the target be? How much should we be concerned if we miss that target? And that brings me to what I describe in my book as the first characteristic of human-induced climate change, and that is that it is all about prediction. It's predictions. Is at the crux of how we understand climate change, because predictions give us a choice. Because we know, or we think we know, something about what the world will look like in 50 or 100 years' time if we achieve net zero, say global net zero by 2050. And we have some understanding of, or we think we have some understanding of what the world will look like if we don't achieve net zero until, say, 2100, or if we don't take any serious action to tackle climate change at all. And it's those different pictures of the world that give us a choice. Which ones do we want? How much are we willing to spend to get them? So these pictures of the world seem to me to be absolutely crucial. And when we think about policy, climate policy, whether it's a matter of keeping net zero in law in the UK, or whether it's about whether we are going to only sell electric vehicles from 2035 or 2030, or whether it's a matter of where we are going to require no new gas boilers beyond a certain point in time. As we're bringing those different pieces of legislation, we need to be thinking about them in terms of what's the consequence of meeting that target or not meeting that target. And we need to be discussing them in that way, because it's very easy for politicians to say, okay, the public doesn't want to get rid of gas boilers, so we're not going to do that because people don't want to do that, or they don't want to pay for that. And that's fine. It's perfectly reasonable to have that view. We should accept that as an acceptable view. But we should be discussing it in terms of what's the consequence of not doing that, because it's not just a matter of saying, I don't want a heat pump boiler. It's a matter of, okay, you don't have a heat pump boiler. Most of our nation won't have a heat pump boiler. What's the world that looks like as a consequence of that? Do you want that? There's a balance here, and you need to get that balance. And that balance comes from prediction. It comes from some understanding of what the future will look like under different policies. And it's science that gives us that understanding. And so it's really critical, not just for building those flood barriers, not just for those engineering decisions, but for the whole of the narrative around climate change in society, to be clear what type of predictions we have, how reliable they are, and what uncertainties they come with. This seems to me to be crucial for a coherent on how far we go on and how quickly you go on energy transitions. So prediction to me is at the core of everything with climate change. And just to say, when I think about predictions, in my world, as in my the people I hang out with, the climate modelers, the people who are working on climate change day in, day out, particularly climate physicists, when we think about prediction, we think about changing temperature, changing extreme temperatures, changing rainfall. Some of us go a little bit further than that into impacts, so changing crop yields, changing heat waves, changing health consequences, vector-borne diseases, and these sorts of things. But I would argue that this prediction ought to go much further than that. This is a matter of painting a picture of what society will look like under different scenarios as we go forward. And that partly comes from the science, but it partly says, well, if you're going to have increasing extremes, you're going to have increasing floods, and communities across our nation, whatever nation that is, are going to be increasingly hit by events that require the government to come in and help you recover, then that's going to be an increasing drain on the economic resources of your nation. And if you're spending money on that, you're not spending money on something else. So the consequences of climate change will then have knock-on effects with the wealth in your economy. It'll have consequences on how much you can expend on education, on your healthcare system, on cultural aspects. So I would argue that the consequences of climate change spread out through society. And when we're thinking about that prediction, that description of what the world will look like under different scenarios of the future, we need to think about it in those wider terms. What are the consequences for the societies and the cultures that we live in? To me, that seems absolutely crucial to engage wider members of the electorate in the discussion, because actually, if you're only going to talk about it in terms of you might get flooded, in my experience, most people think that's not nice. I don't want to be flooded, but I don't think I'm going to be flooded, and they move on. So there's a need for that one issue. Okay, so the framing issue is prediction, and okay, so that's my starting point. In my book, I then go into a series of characteristics and challenges, and there are 7 sort of characteristics I introduce, and I'm going to just talk about 3 of them: extrapolation, non-linearity, and the one-shot bet. So let me just start with extrapolation. So I've said it's all about prediction, but it's a particular kind of prediction, and we need to think about information content here. So you don't really need to terribly care about what the picture is showing here. The point here is that we're driving the climate system from one state into a different state. That's what's happening when we increase greenhouse gases in the atmosphere, because we're trapping more energy in the low atmosphere and the upper oceans. That's what a global warming is. And this time series here is simply the observed time series of carbon dioxide concentrations in the atmosphere over the last 650,000 years. It looks much the same for the last 2 million years. And the point is, throughout that period, it has ranged between about 180 parts per million and 280 parts per million. It's now at above 420 parts per million, and if you account for other gases, above 450 parts per million. And the point here is that human activities have driven those concentrations outside the bounds of anything we've seen over the last 2 million years. And that will change the state. It will change the way the processes in the climate system interact. So we're driving the system into a new, never before experienced state. We have no observations of the climate behaving in the way it is today, or in the way it's going to behave in the future. And that's the crucial thing. The observations we have of the climate are either paleo observations going back 650,000 years, or rather more of them in the last, say, 100 years, which will be in this period when they're rapidly increasing. But we're going to go even higher. So we're taking the system into a state that it's never been in before. We have no observations of that state. And there are 2 crucial things about that. When you start crossing boundaries of points where you get different types of behavior in the physical climate system, that's likely to be happening here, and we don't have observations of those. That means that the observational time series doesn't contain the information about how the climate will behave in the future. That's our coming moment. That's critical if you start to think about trying to use AI or machine learning to make these predictions. It's saying that the information isn't in that data set, so you can't extract it. There may be lots of information in that data set, which if you're clever about, you can extract useful stuff out, but you can't just throw it in and say, here's your prediction. And the other thing, I will come to you in a moment, is that we have no opportunity to verify our prediction. So if you think about a weather forecast, we've got a daily cycle, a sub-daily cycle of making weather forecasts and then seeing the outcome. So to some extent, it doesn't matter whether you've understood your model or your process of making weather forecasts. If it does a good job, you can tell because you've got it every day. You can assess it. But with climate, you don't have that. We're trying to predict 30, 50, 100 years in advance. We don't have any data to verify that process. And we believe it is, many of the processes will be different to how it is in the past. Yes, sorry.
Just to confirm, Earth had this much CO2 3 million years ago in the Pleistocene era?
Yes, and the continents were laid out differently. It's a different planet.
Okay, so
it's not a different planet.
How do we know that the CO2 levels were that high then, and therefore why can we not extract any useful information?
I would not go so far as to say we can't extract any useful information, but we can extract useful information, but we can't see that as a direct parallel for the type of predictions we're making today, because the planet was in a radically different state.
State being
things like layout of the continent. But it's not that there's no use there. So the other characteristic I wanted to highlight was non-linearity. Now, I wasn't quite sure how the audience would, how you guys think about non-linearity. I just want to highlight maybe a couple of things. So when I talk about non-linearity, I'm really talking about chaos, mathematical chaos, essentially the butterfly effect. So there are a couple of things to pick out from here. So if you think, so a chaotic system, a mathematically chaotic system is something like what I'm showing here. This is what's called the Lorentz attractor. And what it is showing is sensitivity to initial conditions. So what you have here is a system which is defined by three fairly simple equations, which I've decided not to show. It's a Lorentz 63 system, so you have three equations, you have three variables, and the equations tell you how each of those variables will change in time, so that if you know the starting values for each of these variables, you can apply these equations and they'll tell you what values they will have in, say, 10 minutes or an hour's time. And then you can repeat that process and you'll get a whole series of these different values of these variables. And so you get a path. You get a path in this three-dimensional space where each of these dimensions represents one of the variables of the equations, and you get this this path that traces out a shape in this three-dimensional space. And this is called an attractor, and in this case it's called the Lorentz attractor, and it's really cool and has all sorts of wonderful characteristic characteristic issues which are just well worth looking into. But the only one, well, two I want to highlight here. One is that while you have this attractor, if you start from any point in space or somewhere near the attractor, the equations will tell you what happens in the future. So you get that red line. So you know, once you've got your equations, that's kind of your model of the world, and you know your starting point, you know what's going to happen. It's all sorted. But the issue in this sort of system is if you don't know that starting point exactly, perfectly. If you have any error at all, then at some point, your prediction of what's going to happen will be wrong. And that's what's happening here with the dashed blue line. You're starting from almost the same point. And for a while, the blue line is very good at predicting the red line. And then at some point, goes, boom, does something else. That's this sensitivity to initial conditions. The other point to highlight here is that each of the variables is sensitive to each of the others. You need to know all of them, right? Now, the reason I highlight that, well, the reason I highlight any of this is that a climate model, when we build a climate model of the climate system, it's vastly more complex. It's got millions of different variables, but essentially it has many of the same sorts of characteristics. It has this sensitivity to initial conditions, and in particular, it has this aspect that uncertainty in any of those variables, or indeed any of the components of the climate system, will impact our conclusions about the rest of the climate system. Which means that to predict the climate system, we need to get it all right. We'll come back to that. So that's something that's not the case in weather. So if you think about it in weather, it doesn't matter whether you've got your ocean circulation patterns, whether you've got your ice sheets, whether you've got your soil moisture and land surface processes right. That doesn't necessarily matter because you're only interested in a part of the system for a short period of time. Basically, as you're going around here, that's your kind of weather forecast. But for climate, you really do. You care about everything, or at least everything could matter. Okay, so that's a few framing issues. So then come to some of the challenges. I'll just talk about a few of these challenges if I get time. I'm going to focus on tying down what we mean by climate and how we relate models to reality. And then I probably won't get to, well, maybe I'll say a few words about social science stuff as well. So just as a starting point, tying down what we mean by climate. If you go to the all sorts of different textbooks and the Intergovernmental Panel on Climate Change, there's lots of definitions of climate. But the definition of climate that I think is most useful when we think about human-induced climate change comes from Robert Heinlein, which is climate is what you expect and weather is what you get. And I think that encapsulates this idea, well, it puts down the idea that climate is a distribution, weather is sort of sample from that distribution. And so there's this is illustrated here, these are temperatures, some temperatures in Perpignan, France, in the 1950s in blue and in the 2000s in red. And you can see that, you can interpret that distribution as climate. So we had a certain climate, I mean, there are certain problems in this, but never mind. Interpreted that way. The distribution of the blue distribution was the climate of Perpignan in the 50s. The red distribution is the climate of Perpignan in the 2000s. And the change is climate change. When you move from one distribution to another, that is a change in climate. So it's not just a change in the average, it's a change in the whole shape of the distribution, and quite how that impacts your decision or how you build infrastructure will depend on what part of that distribution you're vulnerable to. But when we think about climate change, we should be thinking about that change in distribution. Okay. So how do we get that for the climate system? Well, if I step back a moment, the way we tend to make climate predictions, if you take some sort of computer model, these are the sort of big things that break down the atmosphere, ocean, cryosphere, land surface into different grid boxes, and we'll solve lots of equations and parameterizations of all of these grid boxes. And we drive those models with different scenarios of future greenhouse gas emissions, so yeah, these sort of things. And that will give us what happens in the model under that scenario. And what I'm going to call those conditional predictions. They tend to be more usually called projections, and we can have a debate as to whether that's a good thing or not, but I would like to call them conditional predictions. So this is the sort of mechanism or for the models are used. What I talking about here is climate as a distribution, climate is change. Sensitivity to your starting conditions. You have to start these models off for the state of the atmosphere ocean system at some point in time. And if you choose a slightly different state, you will get a different simulation going forward. And if you run lots of those simulations, you can build up this changing probability distribution going forward. So in this case, we've got the global average surface temperature, and now we have that probability distribution. It's messy, but it's a changing. If you cut through this, you will have the sort of PDF that we saw for Perpignan. But now we're seeing that distribution as a whole changing going forward, and that's for the same for Northern Europe average temperatures. So that's something you can do with a model. You can do it by running the model lots of times. And it's worth saying, most of our modelling experiments don't do that. And even this isn't terribly well resolved, but this is one of the few that does. Most of the modelling experiments just don't run those large collections of simulations. So you can't build up that changing distribution. And I would argue that you're not making a climate prediction at all, even within the model. You haven't quantified the distribution. But it is theoretically possible that you can do that. But one of the aspects of climate change or another aspect that one needs to remember is that, so it needs to step backward. That's the best you can do. If we had a perfect model, we could run it lots of times and we could build up the changing distribution for all sorts of variables going forward. That's the best you could imagine being able to do. That's the best possible climate prediction. But in reality, we will only experience one path through that changing distribution. And those paths can look very different. And I just wanted to highlight that. So if we highlight that by looking at the past. So if we look at the last 120 years and we look at global average temperature, this is the time series of global average temperature, and you see that general trend of global warming. That's fine. If you take one of the models, big Earth system models, and you take two simulations. So I'm not changing the model at all. It's exactly the same model. You can think of that as it's exactly the same world that we're looking at. It's just not the same as the real world. It's a model world, but it's exactly the same world. And I'm going to change the starting conditions. When I say change the starting conditions, of the million or so grid boxes that represent this model, just take one of them and change the temperature in that box by 1/100th of a degree and set that model going. You will get a different trajectory going forward that could be as different as this. Okay, it can have massive differences. So the difference here is that on one of these time series, for about 50 years, one of the time series is warmer than the other one, and by at times about 1/2 a degree. Remember, we're trying to keep global warming to less than 2 degrees. So we're talking about something that is a significant component of the change that we're looking at is uncertain simply because we can't know it. It's unpredictable. So there are significant uncertainties as to quite what that path will look like. Which brings me to my third and the last characteristic that I'm going to talk about, which is that climate change is essentially a one-shot bet. The best kind of prediction that we could imagine getting would be this changing probability distribution going forward, but reality will be some particular trajectory through that. And if you just take, I don't have the perfect, I keep thinking of better figures that I should have put in my book, but never mind. If we look at this, the black lines here are the average of those distributions across lots and lots of trajectories for two different scenarios going forward. One of them aiming to limit global warming to 2 degrees, and one of them essentially allowing climate change to continue, basically continuing using green fossil fuels the way we are at the moment, or sort of expanding. So you've got two black lines and they're separated. But then on each of those, I've drawn two different potential trajectories within those distributions around those lines. one of the things is that for 30 years or so, if you got unlucky in a world where you were doing a lot about climate change, you would end up with temperatures that are higher than if you got lucky in a world that's that you're not doing anything about climate change. Now, longer term, they separate out, and it's really clear the value. But shorter term, it's not as clear. Now, this isn't an argument, don't do anything about climate change, but it is an argument when one is discussing it, when you have a narrative in society, you need to be aware that there are these uncertainties and that people will make arguments along these lines that can be reasonable arguments. It's the sort of, there's a gamble here. So the best we can have is a changing PDF, but we will be just one trajectory within that. And that raises questions of how we respond to risk. Now, I believe quite a lot of you are involved in risk analysis, probably know an awful lot more than I do. But it seems to me this is quite moderately unusual aspect of risk. We are used to taking out insurance. We're used to investing in stocks. Maybe some of you are used to playing poker or going to a casino. But we're used to that sort of dealing with uncertainty and making decisions on uncertainty. So I don't think that's an unusual thing. But in most cases, we do it multiple times. You take out insurance every year. You buy a car every now and again. You will change your investments every now and again. Sometimes you're going to win, sometimes you're going to lose. But if you've estimated the probabilities well, then overall you're going to win. That's what you're aiming for, using those probabilities so that overall you'll win. But that's not the kind of way that we need to be thinking about these probabilities, because there will only be one 21st century. That's the outcome we get. We might be lucky or unlucky within the distributions that we choose, but there will only be one outcome. How do we respond to that risk? Does that change our attitude to what risk we're willing to accept? And I don't really know the answer to that. Okay. So the second part, second challenge I wanted to highlight, because I think it's really interesting, and I hope you did too, is a question of how we relate models to reality. Yeah.
Just going back to previous slide, as we go along, can't we inform and see, oh, we're on a lower trajectory, or kind of we maybe overestimated our risk and it's kind of like a constant adjustment game, or if I think does that not work?
No, it doesn't work. I mean, it maybe works a bit, but the timescales of the response tend to be too long to give you a useful feedback. Which kind of comes from this sort of, if you're not going to get any clear signal for 30 years, yeah, no. Which is a bit of a shame. Yeah.
Expected decrease of 1.5 degrees is supposed to happen around 2030, and by 2024 it's somewhat scientifically unlikely. In that regard, we think we are just in a very unlucky world where the trajectory is following a very unlikely scenario, or we are missing something where I don't think we're following the heaviest scenario that we had.
So my predisposition would be to say we're missing something. My belief about something that I'm not discussed and I'm not going to discuss is that actually the sensitivity of the climate system could well be higher than it tends to be acknowledged. But I think it's very difficult to identify whether we can say it's because we're missing something or because we got unlucky. And that feels like a really important part of the discussion. So I was involved in celebrations when the Kyoto Protocol came into force. The Kyoto Protocol was agreed in 1999, I think, came into force 2003, 2004, something like that. Okay. And it kind of felt at that stage that, okay, we've done that. So we've got this sort of agreement. And then you had a decade, a little bit more than a decade, when you could argue that global mean temperatures didn't go up at all. You can argue that that's a misrepresentation, but you could argue that. And I remember being told that there were groups of environmental journalists went to the Science Media Centre in London to be presented information about this at some point, probably about 2009, where you had a group of scientists saying, look, it was always on the cards that it might level off for a decade or so. You know, that's the way the climate system works. But take that in your stride. And what I'm told, I wasn't in the group, but what I'm told is that various journalists then pretty much exploded and said, but you never told us. That wasn't what we understood. We understood to mean we're going to have a steady increase. And we've been fighting our editors for the last 10 years to say, we know this, and you have now completely undermined our credibility. And that's kind of where this is coming from. Acknowledging the uncertainties is about keeping the credibility for the things we know concerned about. We can come back to that because I'm not sure I've completely answered it, but I'm going to plow on a bit more. Yeah, sure.
Yeah. Go back a slide.
Yeah.
So I guess the red is probably an RCP 8.5.
Yes, it is. Yeah.
Okay, so that credibility, you know, RC 8.5 is pretty incredible as a scenario.
Yep.
Given the way the world has evolved in the last 15 years. So same point can apply exactly here. Why are these scientists still putting red curves on here related to 8.5 world, when actually that assumes we're going to triple the amount of coal is going to be combusted, and that is implausible.
Yeah. No, that's fine. I would say I didn't talk about this this slide because I was making those some wide points, but I do have this one on the left, which is this is 2.6 and this is 4.5.
But it's the same point about scientists being credible when they show different types of prediction.
So you're absolutely right. And I mean, my book was published 2 years ago and the plots produced somewhat earlier than that. I think I would be more cautious because this is the plot in the book. So I will be more cautious now. Because I think you're right. But I also have some concerns when I read, when I read information from a guy called Roger Pielke Jr. So most of you will not necessarily know him, but he's a blogger about climate change. I don't know how to characterize his position, but he's made this point a lot about how taking this scenario, which is not really a credible scenario, is misleading. And I think you and he are right about that. But I think there are some types of experiment which are useful to do to understand the climate system by hitting it really hard, because it's a signal to noise issue. So it can be useful to do that because we can learn something about it, which then comes back to the communication thing. So it might have been a sensible scenario to run because we then learn something about the climate system. But if you then take it and present it, possibly as I have done here, to say this is a plausible future world, then that's a misleading thing to do. So, yeah. So the other challenge I really wanted to focus on was how we relate models to reality. And the few things I wanted to raise here. First is just a context. Our models, our Earth system models, fantastic achievements of modern computer-based science, really useful in all sorts of ways, but we just need to remember they are significantly different to reality. So what you will often see is time series like this. This is global mean temperature change over the last 170 years. That line is observations. Lots of coloured lines are the models. I'm not sure you'd necessarily say that they are consistent. I don't think they necessarily are, but they all sort of get that warming towards the end. There's a sense in which they are sort of look kind of realistic. But this is in temperature change. If you look at the absolute temperatures, you see there's actually a range of about 3 degrees in these models. And if you look at a particular region, different regions, I've chosen Central North America, you've got a 5 or 6 degree range in the temperatures of these different models. There's I think annual mean temperatures. Yeah. So there's a crucial issue here. This means that these models are significantly different to the real world. This isn't just within variability. It's not that initial condition, different trajectories. They are significantly off. And in important ways, because if you've got 1 or 2 degrees warmer or colder over some region, then the Earth's surface, the surface processes, whether you've got different types of forests, different types of savanna or whatever it might be, or the amount of rainfall or snow you've got there, those will be simply wrong, in which case you wouldn't trust those sorts of detailed predictions going forward, because it's getting it wrong. Or, almost worse, if you compare those sorts of details to observations, you might think that they look quite good. And if they do look quite good, that's because you have tuned the representation of land surface processes to get something that looks like the right answer with the wrong inputs. And if that's the case, you don't trust the model to provide that sort of level of detail going forward. So I say again what I said at the start, I'm not a climate skeptic, but I'm deeply concerned about climate change. As we know about why warming will disrupt society, we have all sorts of expectations. But if you're trying to build infrastructure and you're looking for what is the temperature be, what's the land surface cover that you need to prepare for, then we've got real problems. These sort of models aren't going to tell you. I'm going to include this. I never know quite where to include this, but I thought this would be, I thought some people in this would like this, so I'd include it. So one of the questions there is, what do you do with those models? The models are well, the big question is, what do you do with those models? These models are inconsistent with reality. How do we move forward? And this is a big thing where I'm getting sort of active in trying to lobby a position. So some people will say, what we need to do is make those models better. We need to get them closer and closer to reality. There's all sorts of reasons why I think that's a bad idea. But what I wanted to do was introduce just one of them with this to raise this foundational conceptual issue of how close to reality do these models need to be able to make the sort of predictions that we want. So when is a model sufficiently realistic to make climate projections? And the concern here is something called the hawk moth effect, named by a lovely lady, Erica Thompson, now at UCL. And she came up with the name hawk moth effect for a concept that parallels the butterfly effect. So the butterfly effect says, if you don't know your starting conditions, you're going to get a different trajectory. The hawk moth effect says, if you've got a slight error in the structure of your model, then your predictions, even of climate, even of in distribution, could be completely misleading. And we don't have good examples of that. I consider the question still open to debate. I think Erica thinks it's rather more sorted, but it's certainly an issue to think of. But we can illustrate it a little bit with this. So this is the logistic map. So you have this, what I've called the model here. Is this formula here, and it's known as the logistic map, and it's an equation from ecosystem dynamics. It's another chaotic system, and what it does is it relates for an ecosystem. If you think about fish in a lake, or rabbits in a warren or something like that, you have a population this season, on your x-axis, and you have a population next season on the y-axis. So if you start off with a small population, next season you've got a higher population. So then we move that down here and say, okay, we've got a higher population. Next season again, we've got higher still, and then it collapses and you get a very low population. That's ecosystem dynamics, stuff that I don't really know terribly much about, but it kind of makes sense that if you've got a small population, you've got growth from reproduction. If you've got a very large population, you've got limited resources, and so the population collapses. So, and like the Lorentz system, lots of groovy things here, but I'm not going to talk about most of them. But that logistic map, this model here, this black line here, and that's what that shows. But imagine that the real world wasn't this model. It was a different system, a system that I've written up there. It's got an epsilon here, so it's got some extra terms. It's only got a small component of those extra terms. They aren't particularly big or important, but this is, imagine if the real world were like that. I think I've called it reality there. So the real world is actually that, but the model is this. But the fact that these two lines lie pretty much on top of each other mean that our model is a really good model. And if you're wanting to predict next season's population, you can use your model. It doesn't matter that it's not perfect. It doesn't matter that it's not more accurate. That's your sort of weather forecasting problem. You can imagine this as weather today to weather tomorrow. So you can have a good weather forecasting model. But that's not our climate forecasting problem. Our climate forecasting problem, it would be to say, okay, let's take a collection of different values of the population this season. Because we have some knowledge, but we have it uncertain. So we have a distribution here, and we're going to use that distribution to say what happens next season, and then repeat that multiple times. So what happens if we do that is and we can do that with our model, and we can do it with reality, because I've decided what reality is. If we do that, then after one season, our model and reality are on top of each other. 2, 3, 4, 5 seasons, great. Our model is doing a super job. But after some period of time, and certainly after 8, 9, 10 seasons, the difference, those small differences between your model and reality lead to you getting completely different distributions. I'm not particularly saying that this model illustrates that this is a problem in climate, or how that would look like, or what that would look like. But it is an issue that we need to be aware of. So when we think about, if we look at our models, our global climate models, and say they're not as realistic as we would like, that's fine. But if we say, well, we're going to make them better, we need to address the question of, well, how much better? When will they be sufficient to the job that we're asking them to do? And I don't think we know how. I don't think we have an answer to that. The Hawke effect would suggest, if that is real, that there might not be an answer to that. And we need to look at different ways of using these models. That's not a good colour. It's a nice yellow on my screen book. And so, just sort of dashing through a few other thoughts. The way my proposals, these are not generally accepted, but my proposals of how we address that is to move away from the question of making our models better, because we don't know when a model is good enough. But we want to change the question and instead try to get a real diversity of models, push our models to do different things. And this is illustrated here with a particular experiment where we took a model and changed how it represented all sorts of things. And what we're looking at here is the change in temperature in response to doubling carbon dioxide in the atmosphere against a change in rainfall in the same scenario for Northern Europe. So all of this tends to focus on regions or localities. And we got lots of different models, different model versions by changing the way the model represented the real world. And the different model versions did different things. Some of them showed increased rainfall, some of them showed decreased rainfall, some of them higher temperatures, some of them lower temperatures. And notably, and as expected, none of them showed cooling. This kind of goes into that what we know area. The You increase greenhouse gases, you're going to get warming, and you're going to get increased warming in high latitudes. This is stuff that we know, that you can track down to the physics. So this is something that's kind of robust. What I would argue for the future of climate models to support decisions in societies, you want to push out those bounds. You want to try to find models that do something different. Because for two reasons. One, when you find you can't push our models to do something, to go into an area of response space, this is a different type of information. It's a different type of evidence. It's not that we just believe in our models. We're saying in the realm of possible models that we think are credible, none of them can go there. And that perhaps lends evidence to the idea that maybe reality can't go there. I don't know if I've got any philosophers in the if there are any philosophers in the audience, but I imagine if there are, they'll probably get a little bit upset. But you can you can jump up later. And then this is something sort of for active debate, and it changes the discussion from when is a model good enough to how unrealistic does a model have to be uninformative about extrapolatory climate behaviour. And that, I think, is where we need to go. So I've used up my hour, which is no real surprise.
Keep going.
Okay. It would be nice to just say a few words. It's sort of I put these two slides in as a sort of placeholder because Sean asked me to say a little bit about that sort of interdisciplinarity stuff. So one of the aspects that I haven't talked about yet is this characteristic 6 that studying human-induced climate change is fundamentally a multidisciplinary problem. So there are issues in prediction, which will come down to climate physics, non-linear dynamical systems, numerical analysis, computer science, but also philosophy of science. They're thinking through to how society responds. So we have impact modelling, we have agricultural science, we have engineering, and also our role in trying to guide society. So the aspects of sociology and have psychology. So what sort of discussion should we be looking for in society? And I see these as all interlinked, where there's a tendency to think that the climate sciences can run their models, can do their science, and then hand over information to society to go away and use. But the complexity of these tasks, the errors in the models, questions of the Hawke-Moth effect, mean that's probably not going to be achievable, which means we need to focus, climate scientists need to focus on the elements of the problem that are going to be most useful for society. Because one of the characteristics I don't mention is urgency. We don't want to just go around the houses playing around with our science the way that we've done it for the last 2,000 years, because we see a problem. We want the aspects of this problem we really want to understand. So actually, a lot of the science should be rather more driven by the questions that matter in society, that matter in infrastructure management, design, adaptation. And so I do see it as a multidisciplinary issue. And yes, so this is something slightly different, but it's kind of related. That partly means acknowledging the sociological drivers of the science. I think something that does frustrate me a little bit is that there's a tendency to say, just believe the science, but the science is something that's developing and ongoing, and science gets things wrong, often gets things wrong before it gets things right. And that's fine, but it's something we need to be aware of. So just to sort of highlight that, because I can see it as a fun thing. This is a picture of the planets from about 140 years ago, I guess, something like that. And you've got Earth, Venus, Mercury, but you've also got the planet Vulcan there. And what happened there was that planet Neptune had been discovered a few years earlier because they'd seen oddities in the orbit of Uranus and concluded, how could that come about? It could have come about because there's another planet out there. So they went out and looked for this other planet and found Neptune. Great success. So then they looked some more and they found oddities in the orbit of Mercury. They thought, well, it worked last time. We'll hypothesize another planet, and we're going to call it Vulcan. and people went out looking for it. And there are a few, not many, but a few examples of people observing Vulcan. Then Einstein came along and with theory of relativity, and that explained the oddities in the orbit of Mercury, and nobody mentioned Vulcan again. But this is kind of what happens in science sometimes. We go down a certain route, and we ought to be reflecting on that. With the models that we're using, are we going down that same route? Are we going down the right route? For something as important for our societies, we shouldn't be just trusting the scientists. We should, as scientists, be stepping back and say, are we doing this the right way? And there are lots of drivers on modelers, on modeling experiments. There are drivers such as most of the big models are developed within individual nations, and individual national governments have a tendency to want to use the model from their country. For all sorts of reasons. But that means no modelling centre wants a model that is vastly different to all the other models, because that would look really weird, and because it would encourage adaptation in your country to be entirely different to the rest of the world. So there are these drivers, despite the fact, so that leads to a kind of groupthink in modelling. It sort of drives the models together in a way that is really unhelpful. And then the other thing, which I'll probably leave as the last thing, I'll leave it as the last thing, is just to comment on the barriers to interdisciplinarity. For someone who has had a bit of an odd career, so I'm a physicist by background, but went into energy systems and environmental management and a bit of consultancy, and in more recent years have published with philosophers and with economists and even with some social scientists. When you try to get research funding to bring these disciplines together, or even try to publish into research, in my experience, that's really hard, because what you get is people, disciplinary specialists, looking at the research and saying, yeah, that's nice, I like that, but I wish it was more like mine. Can we have more my stuff in there? And when that but it always kills a piece of research. So I do feel there's a need to embrace. I'm not quite sure I'm doing quite the job you wanted, but there's a need to tackle how we can go about interdisciplinary research in a really constructive way and create careers for them. Now, hopefully it's better in Cambridge, but certainly my sense at LSE is that it's very clear you need to publish in your discipline. You need to publish in the top journals in your discipline. We will give you extra tick points if you go away and do interdisciplinary research as well. That will be lovely. We like that. Very good. But if you haven't got top journals, articles in the top journals in our discipline, then you're going to struggle with your career. Now that to me is a problem. So I'll leave it there. I think it's just best to leave it there. You'll have questions. Yeah.